So it's still a sad-faced parabola, but now it's starting 80 feet up in the air. So let's say it's off of an 80-foot building. So here's the object. It's being shot up off the top of this building, and then it's coming down. And it's still a sad-faced parabola. And I want to find out when it hits the ground, so I need to find out when the height is equal to 0. Remember, that's the t-axis and that's the h-axis. So I set it equal to 0. And then I'm going to factor it. First thing I want to do, instead of having this huge AC, I'm going to pull the GCF out, which is, again, negative 16. Well, not 16t, negative 16 is all. And I'm pulling the negative out because I want a positive lead coefficient. That's t squared, so that'll be minus 4t and minus 5. So it's partially factored. Something times something equals 0. Do I have to worry about negative 16 equaling 0? Is that going to happen? No, because 16 is a constant. That's never going to equal 0. If it had a t in it, I would consider t equaling 0, but it's just a number here, so that's not going to equal 0. This one, however, this nonlinear piece could equal 0, so I'm going to factor that. Again, it factors pretty nicely now that I pulled the GCF out. The only way to get t squared is t times t. The only way to get 5 is 5 and 1. And I'm going to need a difference of minus 4. How do I get that difference of minus 4?
Negative 5, positive 1.
Very good. The larger one's negative 5, positive 1. So I said each one equal to 0. And I add the 5 to both sides, and I get t equals 5 seconds. And if I subtract the 1 from both sides, I get t equals negative 1 second. This is going to be my answer because I don't have a time machine. I'm not dealing with a negative time. This is important though, so I don't want to just cross this out. And here's why it's important. If I go to the diagram, there's 5 seconds. There's where the object hits the ground below. This negative 1, if I was to continue drawing this parabola, it would cross the t-axis at negative 1. And the reason that's important is if I wanted to find that maximum height, I would do the same thing as I did before. I would take those two numbers, find the midpoint, and I do that by adding them together and dividing by 2. Negative 1 plus 5 over 2 is 4 over 2, which is 2. So at 2 seconds, which is 3 units from there and 3 units from there, so it's right between those two. At 2 seconds, that's when it's at that maximum height. And if I wanted to find that height, I would go to the original equation and plug 2 in. So let's try that. Let's plug 2 in. Negative 16 times 2 squared plus 64 times 2 plus 80. So that's negative 16 times 4. That's 128. So we get negative 64 plus 208. And that turns into, oh that's nice, 144. So that projectile gets all the way up to 144 feet, which is the same as the last problem, except for it had an 80-foot head start. Now how come it only got to 144 with an 84-foot head start? It was going slower. Remember, the rocket was going 96 feet per second. This item is only going 64 feet per second, so that's why it doesn't get as high. So that is the maximum height though. That's how high that thing gets. If we look at the instantaneous velocities for the whole projectile, for each moment in this path, let's go ahead and do that. Again, you guys can get a better idea of kind of how this thing is going. So initially, it's going 64 feet per second. After 1 second of being in the air, gravity has affected it by, remember, negative 32 feet per second. So now it's only going 32 feet per second. How fast is it going when it gets to the top of its peak? What's its vertical velocity up here?
0.
0, right. So at 2 seconds, it's all the way down to 0. At 3 seconds, it's at negative 32. At 4 seconds, it's at negative 64. And how hard is it going to hit the ground? Negative 96. So it's thrown up at 64, and it actually hits the ground faster than it was thrown up. And why is that? Because it started way up above the ground. So it's already going negative 64, but it's still 80 feet up in the air. So that gives it another second to go down towards the earth. And by then, from here to here, it's hitting the earth at a speed of, downward speed of negative 96 feet per second. So there's your instantaneous velocity, 64 to 32 to 0 to negative 32 to negative 64 to negative 96. Here's what I like to liken these problems to, because I would assume most of us have experienced this at one point or another. Okay? Being a kid, jumping off the diving board into the pool. We have all done it hundreds of times, I'm assuming, okay? Jump off the diving board into the pool, jump, boom, all right? How high is the diving board off the water? I don't know, 4 or 5 feet, something like that. Not super tall, but you've done it enough times as a kid where you know that feeling of jumping in the air and hitting the water. And then, someday, one of your friends has a party out at the Coast Guard base, and they have the high platform, the one way up there. And you've done this, and you get bored with this, so let's try this one. And you're way up there. And you jump off, and you're like, right about here, you're like, I immediately regret doing this because you hit the water, boom, so much faster. Why? Because you're in the air and gravity is pulling on you faster and faster and faster. So you're not hitting the water at negative 32. You're hitting the water negative 64, negative 96. If you're jumping off of a cliff, you're cliff diving, as a guy, has anyone ever cliff dove in class before?
Yes, not in class, but
No, not in class. Good call, not in class. Thanks for the English correction, I needed that. Well, Max, I think you're the one guy. Max and Dylan, you two guys right now. If you learn nothing about math today, learn this. If you go cliff diving, you don't land like that. Because when you're going and you're hitting the water with a velocity of negative 96 feet per second, it does not feel good on the groin. Keep your legs together, maybe even crossed to protect your region, all right? Because that does not feel good from a cliff. It's okay from the diving board because you're not hitting the water that hard. But when you're on a high dive or a cliff, you jump and you go wham! You go so much faster because you're in the air for that much longer. You can feel that gravity really take you when you jump off of a higher platform. So beware of that, all right? So that's the projectile stuff I wanted to talk to you guys about today. Dive boards, all right? Questions on any nonlinear questions? Any nonlinear problems, you guys?